Hi guys, Gibson here. I'm going to record a lesson for you. This will be the last lesson on this unit of exponential and logarithmic functions. And this one is about what we call a natural logarithm and its base, which is the number e, the constant e, sometimes known as Euler's number, and where that number comes from. So let's look at our objectives for today. First one is to understand where this value of e comes from and what it really represents. Second objective is how do we use natural logarithms? And then the third is to look at a particular example of what we call continuous growth here, which is what the base of e represents in a financial problem, calculating compounded interest. Okay, so let's jump into the lesson here. So let's define this constant e. It's an irrational number, and it has kind of a unique value. It's a 2.7183, but again, because it's irrational, it's going to go on forever. We use the letter small e as the symbol to represent this number. And we use this number as the base of an exponent when we have continuous growth. Okay, now I'll talk about what do we mean by continuous growth here on the next slide. But think of e as one of these top 5 numbers in mathematics. Of course, 0 and 1 are kind of some famous numbers that have some unique properties. Pi you've worked with since early in your math education. This year we introduced the concept of an imaginary number I when we studied quadratic functions. Well, to these 4 we can add e, Euler's number. So let's talk a little bit about the difference between continuous and discrete growth, because we use this base of e when we have continuous growth. So really all the examples that we've studied and modeled so far have been discrete growth. So what do we mean by discrete? Let's look at this example. If we had bacteria that started with 1 and it tripled every day, we'd start with 1 and then 3 and then 9 and then 27 and then 81 and so on, right? We've done examples like this a lot in this unit. So if we graph that, what would it look like, right? We'd have these points here on the graph and they would form this nice exponential curve that we've been working with. Now, up till now, right, we've always kind of fitted a curved line through those points, but the reality is the way we're modeling this is we would start with 1 bacteria, nothing would happen for a full day, and then at the end of that day, we would all of a sudden jump up to 3, right? And then we would stay at 3 for a full day. And then at the end of the second day, we would jump up to 9. And so on, right? We'd go from 9 to 27, and then 27 to 81. So the way we've modeled this really kind of assumes that nothing happens in between the periods, and then as we move from one time period to another, that's when the increase or jump occurs. So we really get this kind of stepped type of response when we model what we call discrete growth. Discrete meaning 1 step at a time. Okay, so when it grows, when we have discrete growth, we can see the change after a specific event or time period. Now, if we were to look at a graph and we started with 1,000,000 bacteria, we know that not all those bacteria would reproduce at the same time intervals, right? Over time, at any instant, some portion of those 1,000,000 of bacteria would be reproducing, right? So this would produce what we call continuous growth. That growth is always happening at any instant in time, and we can't really point to a specific event or time at which the change occurred. So certainly the larger the numbers in our population, the more and more it looks like continuous growth. So how would we model this with this continuous growth function? Well, here's what it would look like, right? If we started with 1,000 on here, let me get my annotation up if I can get that. There we go. If we start with, I'm sorry, 1,000,000 as our starting point, right? That's our A value. And then our growth rate, we're going to use this constant E, okay? Which again is just a number value, 2.7, and then decimals continue on. So in summary, here's kind of what the difference would look like, right? Discrete growth, here's a growth factor of 2, which means we would double each time, right? And here you can see the steps that we take as we grow discretely with each time period. Continuous growth, we use the base of E, 2.7182 as our growth factor. And you can see that this produces a nice smooth curve as we grow on a continuous basis, instant by instance. Okay, so that's the big concept here of why we use E when we're modeling continuous growth. So if we write an exponential function that has E as our base, right, up here at the top, then we can also rewrite that in logarithmic form, right? So E would become our base of the logarithm, X is our exponent, and then Y is what we're taking the logarithm of. So if you recall, when we had 10 as our base for a logarithm, we called that a common log. We also have a special log when we have E as our base, and we call that the natural logarithm. Okay, so if the logarithm has E as its base, we can call that the natural log or natural logarithm. And we can always write it as I've shown here, log with a small e as its base, but you're also going to see it written this way. And the letters are actually an L. I know it looks like a 1, but it's actually an L. That stands for logarithm. And then the N stands for natural. So if you see on a problem where you have this Ln, what it's saying is take the natural log. In other words, E is our base. And if you look on your calculator, so take a minute to do that, see if you can find the natural log key. It should be right next to the common log key. And also, if you look above it or nearby, you'll see another function that has E as the base raised to the x power. So we'll actually be using those functions on our calculator as we work on some of these types of problems, okay? So big idea here, natural log is a logarithm that has E as its base. That's the big concept. All right, so what does the graph of this look like? Well, remember how we would graph regular exponential functions? We really only just need 1 or 2 points to be able to sketch them. And the points that we always want to graph are 0 and 1. So what happens if we put in 0 for x? Well, anything raised to the 0 power will always give us 1. So no matter what the base is, whether it's e or any other value, we would always get 1 for y. So let's plot that here on our graph. Let's do the same if we put in 1. So e to the first power is simply going to give us the value of e. And that value is approximately, right, 2.7183. Now, if you want to be able to get that number on your calculator, just take your function e to the x and put in 1 for x, and that will give you the value of e. So let's plot that, okay? And then we could take e and raise it to the second power, and that would give us about 7.4. So we can plot that. So here's what the graph would look like. It would still go through 0, 1, and then curve up. The first point would be through 1, and then 2.7183, the value of e. We would still have a horizontal asymptote right on the x-axis. So take a minute with your calculator, see if you can take e and raise it to these other powers. You're going to have to be able to do that to do the homework associated with this lesson today. So I'll just pause here and let you see if you can find that on your calculator. Again, if you're using your phone, often you'll have to turn it sideways or do something else to access the more advanced functions, but you should be able to find the e to the x key. Okay, hopefully you've been able to do that. So e to the fourth should give you this, 54.5981. We're just going to round to 4 places here. E to the -3, so negative exponents work, gives us a decimal less than 1. E to the 1/2 gives us this value, 1.6487. Okay, so make sure you know how to use your calculator to take e and raise it to any power. All right. By the same manner, I want to make sure you know on your calculator how to take the natural log of a value. So really what we're asking is e to what power gives us 20, okay? So again, find the natural log, ln, key on your calculator, and take the natural log of 20. So if you do that, you should get this value, 2.9957. So what that's really saying, right, is e raised to this power would give us 20. How about natural log of 1? So e to what power would give us 1? So think about that one actually before you plug it into your calculator. What power do we raise e or any base by in order to get 1? Now, if you said 0, that's correct, right? The natural log of 1, or the log of anything, actually, any base will always give us 0, right? We could write it this way. How about this case? And this one will be important, you'll see in a minute when we start to solve equations that have natural logs in them. So natural log of e to what power gives us e? Well, what would we raise e by in order to get the value of e itself? 1 would be the answer, right? E to the first power gives us simply e. Any base to the first power gives us the same value of that base. Okay, so make sure you're able to access your calculator and take the natural log of these functions. All right, so all those properties that we learned for logarithms also apply to natural logarithms. So I'm just going to go through some quick examples of what some of those properties look like when applied to a natural logarithm. So here's the first one, right? 3 times the natural log of 4 minus natural log of 8. So if I ask you to simplify that, what properties would we use to be able to write that as a single logarithm? I'm going to put my pointer on here. So we're subtracting, right? So that's going to give us the quotient property. And then we have the 3 out front, which we want to move to the back, or back inside the logarithm. That would be the power property, okay? So if we go ahead and do that, we'll use the power property first, move the 3 back inside the logarithm, and then to combine these into a single logarithm, we would have natural log of 4 to the third divided by 8. Now, these are all numbers, so let's see if we can simplify that, right? 4 to the third would give us 64, and then 64 divided by 8 would give us 8. So we do the exact same things that we did with any other logarithm, whether it's common log or log of a specific base. We do the exact same thing if it's a natural log. How about, let's try a couple more of these. Natural log of 2 plus natural log of 4. And this will actually be some good review of these properties. It's been a few weeks since we've worked on these. So what would that give you? Natural log of 8, right? We multiply the 2 and the 4 together using the product property. How about this one? Natural log of 5 plus natural log of x. Well, we're going to multiply, right? The 5 and the x. So we're just going to get simply natural log of 5x using the power property. I'm sorry, product property for that. That's a typo on my slide. Let's try another one here. Natural log of 12 minus natural log of 6. So we would use the quotient property for that. 12 divided by 6 will give us natural log of 2. And one more here. Natural log of x minus natural log of y. Again, we would use the quotient property and just write it as natural log of x divided by y. Okay, so simplifying logarithms, even if they're natural logarithms, we use the same 3 properties, we use the same process. Let's look at expanding a logarithm, right? This is, again, using the properties, but writing a logarithm as 2 or more from a single logarithm that we're given. So we've got natural log of 4 x to the third divided by y, right? So what properties will we need to be able to split this up? Well, how many different logarithms are we going to have here, right? We've got 4, and we're multiplying that times x to the third. So those we can split up using the power property, and then we're dividing by y, so we can use the quotient property. So we should wind up with 3 logarithms here when we expand it. So let's go ahead and do that, right? First, we'll break it up into natural log of 4 plus natural log of x cubed. And then since we're dividing by y, we're going to subtract natural log of y. And then let's move the 3 right to the front. So we'll use the power property for that. And we get natural log of 4 plus 3 times natural log of x minus natural log of y. Okay, so same thing when we're expanding natural logarithms. The properties work the same way. So let's try a couple of these real quick in your notes. Natural log of x divided by y. So quotient property gives us natural log of x minus natural log of y. Natural log of 3r to the 4th. So I want you to think about this. How many logarithms will this give us? We have two factors, right? 3 and then r to the 4th. So if we separate those using the product property, and then we'll move the 4 to the front using the power property, and there we have our answer. Okay. Right, let's try a couple more here. Natural log of 6 over 11, all raised to the 5th power. So quotient property says we can write this as 2 logarithms, subtracting 1. Notice we'll apply the exponent of 5 to both since it was outside the parentheses. Then we'll use the power property to move the 5 to the front. So here's what our final answer would look like. 5 natural log of 6 minus 5 natural log of 11. And let's do one more here. Natural log of 7m to the 4th n squared, or divided by n squared. So again, how many logarithms will we have when we expand this? Well, we have a factor of 7. We've got m to the 4th. And we're dividing by n squared. Right? So we will have 3 logarithms. So let's separate them out into those 3 using the product and quotient properties. And then we'll move the 4 right to the front using the power property. And now we have our final answer in expanded form. Okay, so nothing new here other than we're using natural log, which has a base of e. But everything works the same way in terms of how we apply properties of exponents or properties of logarithms. I'm going to skip past this one real quick if you want. If you can pause this. Okay. All right. So how do we solve equations that have natural logarithms in it? So let's say we have this as our equation we want to solve. Natural log of 5x equals 3. Now, do you recall how we solve logarithmic equations? The answer is we want to rewrite it in exponential form. Okay. So we need to know what our base is. Well, since it's a natural log, our base, right, is going to be e. So we just simply want to rewrite this with e as our base, right? 3 is the exponent, so e to the 3rd equals 5x. And now we can solve this using our calculator. So again, we'll have to say, what is e to the 3rd power? Use your calculator to do that. And we get a value about like this, 20.0855 equals 5x. And then we can simply divide by 5 and we get our answer. Okay, so solving the logarithmic equation, same strategy, rewrite it in exponential form, but we're going to use a base of e and then use our calculator to evaluate that. Let's try another one here. Natural log of 2m plus 3 equals 8. So again, our first step will be to rewrite it in exponential form. So we're going to use e to the 8th power equals 2m plus 3. So e to the 8th, that's going to give us a fairly large number, right? If you think about that, 2.7 raised to the 8th power. So I'm just going to round that off to 2,981. But now we can solve for m, right? What do we need to do to get m by itself? Well, we're going to subtract 3 and then divide by 2. And we get our final answer. Okay, so another example of how to solve a logarithmic equation. When we have a natural log, rewrite it using e as our base. Now, what if we have an exponential equation that we want to solve and it has a base of e? Well, what's our normal strategy here? To solve the exponential equation, we want to take the log of both sides. Now, all the problems we've done so far, we've always taken the common log of both sides, simply because we're able to do that on our calculator. If we have a base of e, in theory, we could take common log of that, but if we take the natural log of both sides, we can still do that on our calculator, and as you'll see, it will actually cause some things to drop out of the equation and make it very easy to solve. So let's do that. Take the natural log of both sides of the equation. So here's what it looks like, right? Natural log of e to the x plus 1 equals natural log of 30. So natural log of 30, we can do that on our calculator. What do we need to do next? We need to get the x plus 1, right, out of the exponent by using the power property, right? We want to take this and move it to the front so that we can then solve for it. Okay, well, there's my arrow, kind of an arrow. I better stop. All right, so let's do that. So let's move the x plus 1 to the front. So we have x plus 1 times the natural log of e equals natural log of 30. Now, let's think about what we said earlier in the lesson. What is the natural log of e? In other words, e to what power gives us e? Well, hopefully you're thinking, Gibson, it's 1, right? So if we know that natural log of e will always give us 1, then when we wind up with this in our equation, right, we can basically replace natural log of e with 1, and it drops out of our equation. Now we have a simple equation we can solve, right? Since we can basically get rid of the 1, all we have to do is subtract 1 from the natural log of 30, and the rest is calculator work. We get an answer of 2.401. Okay. Let's do one more example here of solving an exponential equation that has e as its base. So we have 7 times e to the 2x equals 21. Now, before we take the natural log of both sides, right, we want to isolate the base and its exponent. So we need to divide both sides by 7 first. So let's do that. So we wind up with this, e to the 2x equals 3. Now we can take the natural log of both sides. We're going to then move the 2x, right, to the front using the power property. So here's what we wind up with. Now, what is natural log of e? That's going to give us 1, right, which basically allows that factor to drop out of the equation. So we're left with 2x equals natural log of 3. So we'll divide by 2, and the rest is calculator work. We should get 0.5493. Okay, so a couple examples of there, how to solve an exponential equation when our base is e. We take the natural log of both sides, and we'll always wind up with this term here, natural log of e, which will just simplify to 1 and make it really easy to solve for x. All right, last part of the lesson here. We're going to look at a case of what we call continuously compounded interest. So as you are probably aware, if you give money to the bank in a savings account, they will pay you interest on that, right? Normally, the interest is paid discretely. In other words, they would pay you interest on usually a monthly basis. At the end of the month, depending on how much money you had kept in your savings account, they would pay you interest on that. What if they paid you interest on a continuous basis? If you can find a bank that'll do this, definitely that's where you want to keep your money. You're going to earn more of that. But let's see how this formula works. Sometimes we call this the PERT formula, P-E-R-T, because that's one way to remember what the equation looks like. So what do all these variables stand for? Well, go think of our normal form, y equals a times b to the x. They have the same meaning. A is going to be the amount that we're going to have in our account at the end of some period. P is what we call the principal. That's the starting amount that we put into our bank account. E we know is our base for continuous growth. R is the interest rate in decimal form. And T is the time in years, okay? And we notice when we have our interest rate as an annual interest rate, then the time period has to be in years, right? So the units of measure for time here have to match up. So annual interest rates means how much interest would they pay over a full year? And then we have to have our time period in years. All right, let's see how we could apply this to some examples here. Let's say you want to know how much you'll have in your account after 5 years if you deposit $1,050 and you earn an annual interest rate of 5%. Now, nowadays, you can't really get 5% on an interest on a bank account. Interest rates are very low. That's good if you're borrowing, not very good if you're saving. If you have a lot of money in savings and relying on the interest there, you don't get a lot of income for that. Okay, but let's go with the 5% example here. So our principal, remember, is the amount we start with. That will be $1,050. Our interest rate is 5%. But remember, we want to write that as a decimal value. So how do we take percent and convert it to decimal? We divide by 100. So you got to remember to divide by 100 when you're doing these problems. And we now get our interest rate in decimal form, 0.05. The time in years is 5 years. And now we can plug those into our equation. So here's what it would look like. We're going to put 1,050 in for P, 0.05 for R, and then 5 for T. So we're going to multiply these two values together in our exponent before we use that to raise E by that amount. So if we do that, right, we multiply those, we get 0.25. Now we can use our calculator. What is E to the 0.25? We get this value, and then we're going to multiply our principal by that, and we get our final result, $1,348.22. So if we started with 1,050, we would earn almost $300 worth of interest over the year if we left it in the bank. Pretty good return on our savings account. So let's do one more here for practice. Same type of problem, just different values. See if you can go ahead and set this up. We're going to put in $1,300. So that's our principal. We have an interest rate of 4.3%, and we want to know how much are we going to have at the end of 3 years. So go ahead and pause this, see if you can work this one out in your notebook, and then restart it here, and I'll walk you through the solution. Okay, here we go. Principal is 1,300. Interest rate is 4.3, so hopefully remember to divide that by 100. So we get 0.043 in decimal form, and we have 3 years as our T, or time period. So let's plug all that in. We get 1,300 times E to the 0.043 times 3 as our exponent. So now the rest is just calculator math. We raise E by that power, and we multiply, we get $1,479. So in this example, we would earn about $179 over 3 years. So one more type of problem we can do here. Let's say we know at the end of the period, we want to have $1,000. So that would be our A value. How much would we need to put in 6 years from now? So that 6 years from now, we would have $10,000 if we have a 4% interest rate. Okay, so in this case, we're having to solve for the principal. How much do we need to put in at the beginning? Okay, so let's go ahead and lay this out. P is our unknown. R is our interest rate, 4% or 0.04. The time is 6 years. Okay, so let's plug all that in, including the amount, into our equation. Now, since we want to solve for P, let's go ahead and rearrange the equation before we plug our numbers in, right? So if we want to get P by itself, what do we need to do? Well, we need to divide by E. Let's get a different color here. We want to divide by this whole thing, right? If we divide both sides by E to the RT, we would get this form. Now we can just plug our numbers in and solve for the principal. Okay, so let's do that. We put in 10,000 and then divide by e raised to this power. So now this just becomes calculator work. Make sure you put parentheses around this whole thing in your calculator before you divide, right, the 10,000 by that. So if we do that, we get this amount. So if we put in $7,866 today, in 6 years, we would have $10,000 available for college. All right, one more example. Here we're going to solve for what the interest rate would be. Okay, so this is kind of the other case. How do we solve for the R up here? Okay, and we're given all the other values. So 1,000 is our principal, 5 years is our time period, and the amount we have in our account after 5 years is given here. So let's list what we know and what we don't know and plug all that into our equation, right? So here's our amount. Let's go back to my pen here. So here's our amount. Here's our principal. Notice we put in 5 for our time period, but R is what we are trying to solve for here. So here's what we want to solve for, okay? And notice we're using E again as our base because it's continuous interest growth. All right, so first thing we want to do is get the base and its exponent by itself. So we're going to divide by 1,000. So now we have an exponential equation with E as our base. Well, how do we solve for that? We did a couple earlier in the lesson, if you remember. We're going to solve it by taking the natural log of both sides. So we do that. We're going to bring the R to the 5th, right, to the front. I'm sorry, R times 5 in our exponent to the front using the power property. And then remember, natural log of E is 1, right? So we can get rid of that. It's just going to give us a factor of 1. So now we're left with this equation. Natural log of this decimal is 0.4, and then equals 5 times R. So what's our last step? We want to divide by 5 to get R by itself. And if we do that, we get this decimal value, 0.08. Now remember, that's our interest rate in decimal form. So we could say it's 0.08. If we wrote it as a percentage, we'd want to multiply now by 100. So we could also write it as 8%. Okay, so there's 3 examples: how to find the amount, how to find the principal, and in this last one, how to find the interest rate. You could also put a problem together that gives you the rate, but ask you the time. It would look very similar to how we solved this one for the rate. Okay, all right, so that's our lesson for today. You now know why we use E for continuous growth, what the difference between continuous and discrete growth is. We've looked at how we use natural logarithms. All the properties still work the same. And then we looked at a specific example of continuously compounded interest formula, the PERT formula, and how to use our tools to be able to solve for any one of the variables there. Right, that's our lesson for today. If you look in Google Classroom, you'll find the worksheet assignment that has some practice problems in each of these areas. Thanks.